Okay, I'll wait till people start to get on. I'll get everything loaded up while I wait for anyone who wants to watch. This is going to be a how-to video. All right, let us start building moons. This is actually going to be how to build a moon/ring system, but I think everyone can figure this out. So first off, we need to figure out what planetary bodies are going to work. Let's name this for now A1. And this is a planet that needs to have a certain mass of... It's going to have it in terms of Earth masses. So 3.91264 e to the -7. Okay, that's typical. It usually changes it to something more reasonable. So now, I'm not sure if I'm going to be able to get the densities to be exactly what I have down on paper, but this should be a moon that is primarily made up of water. We're trying to get down to a density of 1.27, but it looks like within this game, without me adding any hydrogen to the mix, the lowest I can get is to a density of 1.29. And that's fine. If that's what we have, that's what we have. Now, one problem about this is it's not going to let me adjust any of these until I've created them and saved the game. So here's what I'm going to do. I'm going to create them in just random orbits, name them what they need to be, then save and reload. A2. And this is going to be a similar situation, but I won't be able to get it down to the density that I want, where it's primarily made of just water ice with some impurities, meaning it's a dirty snowball. So we're going to get it as close to what I show on paper as possible. So it's Earth its mass in terms of Earth masses is 1.63721. The reason this is important is this mass, when I configure the density, it will give me approximately the right radius. Yeah, I can't get it any less dense than that. This is the least dense it can be. I might need to change all of this. If I remember correctly, I wasn't able to get any of these densities accurate. Yeah, I had to make all of these out of iron. But I'm okay if I have to do that again. Yeah, these aren't supposed to be iron. And you know what? I'm a forgetful person. That's what we're going to have to do with all of these. All of these are going to have to be made of at least iron, because iron will not break apart due to the physics of the game. Is that the right mass? Yes. It's not going to be the right radius, but it's going to be the correct mass. Let's see, what's the radius? Yeah, that is almost less than half the radius of it, of what it's supposed to be. But you know what? That's fine. So I forgot that that's what we're going to have to do. Is just make them out of iron. In real life, these objects would stay together within the Roche limit due to the tensile strength. Not gravitational bonds, but the bonds between atoms themselves. Because all of these objects are going to be so dense, or so, not dense, the opposite of dense. They're going to be very, it just seems like English doesn't have the right word that I'm looking for. They are non-dense. They are like water. Water is only one density. And they're going to be within the limit that if they were held together by gravity, they just break apart. Plain and simple. But these are objects held together by their tensile strength. That's the only reason they can exist within the Roche limit. The other way they could exist within the Roche limit is if they were made up of something denser than water. And in this game, you can make them out of iron, and that has a Roche limit much closer to the host planet. Okay. Just checking my Twitter. Alright, so we have this. We need to rename it. So this is Renault A3. Give it the correct mass. And we're not going to worry about configuring what proportions of what elements are in there, since that would just cause it to break apart. And our goal is to keep these together make it seem like it is a doable ring system and moon system. 2, 8, 6, echo 7, -7. All right. There that is. On to the next one. The last of our inner moons. We're now A4. This is going to be a much less extensive ring and moon system than the previous planet, because the previous planet is a lot denser and its mass is much greater. Okay. Not moon, Earth. So this is 1.39027 echo -6. And making sure this is made out of iron only. Okay, so that's our inner moon system. Let's do it steps at a time. Save the simulation. Copy over the previous. Let's not make mistakes. Make a new, call it test, copy over our previous test, and here we go. Let's reload test. And there we go. This is the beginning of our inner moon system. Now I need to readjust all of these moons to get them in the right position. And let's see, I need to make sure I have everything on paper down in front of me. So we're going to start out by changing the orbital dynamics. Let's change, go to meters. On paper, I should have put commas here to make it clearer. 65, ot. Maybe I should have just kept it in kilometers, but I wanted it to be more accurate. And then just for right now, because we need to be able to adjust both the argument of periapsis and the right ascension of the ascending node. Both of those we need to be able to, we have to adjust the argument of periapsis, which is why we're changing the eccentricity to 0.02. It's just because the numbers that I have on paper, I don't know what they would be converted to if the eccentricity were 0. So the number that I have on paper is an E that's very close to 0. And Universe Sandbox isn't going to let me enter in 0.000001. It's going to round it down to 0. And then I won't be able to get it exactly in the position that it needs to be. Well, what I'm trying to do is get it as close to the position that it would be in real life, which means I have to change that to 0.02 eccentricity, and then change that at the very end to 0, like it will be. If I were to enter 0.5 zeros and then a 1, it would just round down automatically, and then it'd be messed over. So our argument of periapsis, inclination is the next one. 24.56, let's see, yeah, that rounds to 1 digit, and that opens up the right ascension of the ascending node, which I also need to edit that. So note to self, 24.6 is the number that we'll have to use for all of these values. So the argument of periapsis is next. 23.53, probably rounded to 1 digit. Okay. Now it looks like it's moving around all over the place, and that's what it's supposed to look like it's doing for right now. We're getting it into the position that it will be. And then this number is crucial. The right ascension of the ascending node. 115. 115 degrees. Yep, it jumped all the way over here. We're almost done. And since we are going to have the mean anomaly is going to be based off of 0. So before I change the mean anomaly, I'll go ahead and just update the eccentricity to 0. And now I will change the mean anomaly. And since the eccentricity is 0, for right now, we'll just use our true anomaly, which is used to calculate the mean anomaly. So 41.2, did it? Okay, it did. It changed on me. That's good. That's what we want it to do. So now it is in position. If I were to look at this, the orbital plane should be over the equator of Renal. I have no easy way to figure out exactly what the orbit is going to be around the equator. But one way I have found out to do all of this is to go to a planet and go to add ring. Any of these that creates it over the equator of the planet. If you were to go to add ring, now you have a ring. It's not very visible, but there are pebbles in here. And you can click on one of the pebbles in the ring and convert it to a full body, and then go to its statistics. And you won't be able to see anything. But if you were to save and then reload and look at that body, you will be able to find out its orbital elements. And the orbital element that's most important to get this to work is the right ascension of the ascending node. I went through this, clicked over now, and figured out the right ascension of the ascending node needs to be 115 degrees. The other orbital elements don't matter. Well, they do matter. The orbital elements that matter are the right ascension of the ascending node, I misspoke, and the inclination. Those are the two things that need to be exactly 115 degrees and 24.56, and these don't have orbital statistics yet. Now there is one that will, and if I were to save, let's call this test 1. And then if I reload test 1, there's this small nameless pebble, and it has orbital qualities now. And you look at this, it has an inclination. Well, that's not matching up with the number that I have. Why doesn't that match up? $22.4. Huh, my numbers are off here. I have to recalculate. So this is 20, this is 22. Okay, so I have to make a change on the fly here. How did I mess that up? $22.4, right? Alright. I'm having to make some changes to the rest of my numbers on the fly here. Everything is going to be off in the inclination by about 2.16 degrees. Negative 2.16 degrees. Everything needs to have 2.16 subtracted from it. Okay. We are going to start over within test. And redo some numbers here. Sometimes even the most precise things can end up being inaccurate. Moral of the story: check your numbers before you live stream. At least I had the 115 degrees correct. Let me just check a number here. No wonder I was using the obliquity, but the obliquity is adjusted by a constant that I don't know. And then this is 22.4. Argument of periapsis will be 23.5. Sorry, I need a drink. The right ascension of the ascending node. Then that is 0, and this is the true anomaly is for 1.2. So the rest of these numbers would change due to this eccentricity being 0 now. And this is going to be taken into account by changing the other numbers. Probably the mean anomaly will change and be adjusted because eccentricity 0, the argument of periapsis, will be something different. Okay, so now we have it in its final position. We tidally lock it. And now we can move on to the next moon. And this is how it's going to go for the inner moons right now. Now these inner moons have these other inner moons have slightly more calculated values to their distances. Yeah, I figured that would truncate some of those digits there. Okay, the eccentricity for right now, 0.02. The inclination of 22.4. The argument of periapsis, 179.87. Woman 5. And let's change this to 0. And this is 179.87, which is just 180. See, they are really close to each other. And then we orbital lock it, or tidally lock it. And that moon is now done. Okay, on to now 3. So it is 75, 425, 818, which gets rounded up to 0.9 or 819. Okay. Eccentricity of 0.02. Inclination. And then the argument of periapsis is not 167. And now the important number 115. The second important number. And finally, the last 2 changes. $351, which will round up to 352. I guess that's too close for the orbit to show. I'm not sure. But we know that that is where it's supposed to be. Almost forgot my last step. Tidally lock. And there we go. Now on to the last of these inner moons. $787.41893 meters. And then for right now, put it at 0.02. Inclination of 22.4. And what did I put the argument of periapsis as? 287.99. Okay, that's going to round up to 288 degrees. Now the other important number that we'll put it in the same plane as the other moons, 115. Zero for the eccentricity, and now we have the true anomaly is 140. Okay, so those are all completed. Now it's time to save. Save it under test. Yes, replace. And let's reload. That looks messy there. And it only registers 2 of the orbits for some reason. Bear with me a moment. Yes, that was Pokemon Go in the background. And I do still play that. I just got a Pokemon back from a gym. So, just a moment, sorry. Okay. And now there's some Pokemon invading my house. Okay. Alright. Where was I at? We just got done with these inner planets. Bear with me a moment. I'm just making sure my numbers in the next few parts work out. Okay, so what is next is adding what I will label B-type moons. These will be the major moons of this system. I don't know why I clicked there. So, to add major moons, we can just add a small random moon and reshape it. Okay, I'm okay with that texture. I'm just going to randomize it. We're going to call this Renown B1 for right now. That's a perfectly acceptable name. And then in terms of Earth masses, what do we have here? 0.02450816636. As long as we want to keep these moons less massive and then like it's a very small percentage of the mass of the planet that it revolves around. That's under the assumption that these are in situ moons. If these are captured objects, they can deviate from the normal mass that would be considered. Now this is one where I'm going to mess with I can't think of my words today. I'm going to mess with the density to make sure it's correct. So the radius, yeah. We need to mess with the amount of iron, silicate, and we need more water. That's close to the density that I want. So I'm going to take away a little bit of water and just a tiny bit of iron. And that's what we want. So the composition of this is mostly water ice. And we're at 2.1. That was too much iron. Let's take away a little bit of water. No. That's what we want. 2.18. And what is the radius in Earth? In Earth radius, it's 0.19. Okay, calculated value is 0.18. That is nearly perfect. On to the next moon. We're now B2. So here we go. The mass in terms of Earth mass. So it's best to have it less than 1,000th of a percent. Am I thinking of that number correct? The mass of this planet. This is 30 Earth masses. This is going to be much less massive than that. Point 0.002324728, and I'm not sure when this is going to round off, so I'm entering the entire value. Okay. It cuts it off after about 5 significant digits. Good to know. And then I want to get the density to something close to what I have on paper. Sorry about that popping noise. Let's leave about 2% iron in here. Like just blows right past. Okay, now let's add water. And I'm trying to get this at about 2.34 grams per cubic centimeter. That should give us the right radius for this planetoid, this moon. Add a little bit of water back in. Add some more silicate. It doesn't look like it jumps right past the 2.34 and just goes to 2.38. I'm satisfied with that. That's close enough. But now this is this. Or now B2 is done. Let's add the next moon, the next major moon just a random body. We'll rename it and restructure it. I don't have very creative names. B3. And the mass in terms of Earth masses, like I said, it's probably 1,000th of a percent, but I forget the number there. It's like 3 zeros and a 1. But we have to have it a lot less massive than the main body to make it anything realistic. And this is 0.00203680069. Let's see, yeah, it cuts it off at 5 digits. Keep that in mind. Leave everything but a little bit of iron. We're looking for a dirty snowball. Well, a little bit more than a dirty snowball at this point, but it's about 2.25%. Or 2.25 grams per centimeter. Oh, just passed it. There we go. Let me just make sure on this. Earth radius 0.170 on mine, 0.171 here. That's as close as we're going to get it. On to the next moon. This one, we're going to name it Renault B4. So Renault B4, Earth mass. It's going to be 0.0014. 6. Everything but about 3% iron, and then let's see. Did I just enter in the wrong value for the Earth mass? Nope. Okay, so this one, we can leave a little bit more silicate and iron in this one. So this one needs to be a density of 2.83 when we round off. It's going down. Let's remove the least dense substance. Maybe I had too much. I'm having trouble with this one because it's a lot denser. Oh, there it was. And that's the right value. And the right, yeah, it's 903 kilometers. Yeah, it's the correct percentage of Earth radii. Random moon next. Okay, so this one is going to be not Erdis T. I'm going to call it Renault B5. Okay, so let's just edit everything from this screen. Earth masses. .00135. Did I just delete it? Yeah, I totally just deleted it. Must have hit backspace. No problems. Okay. How many Earth masses? .00135. There we go. And how many grams per cubic centimeter? Okay, so this is at 0.44%, or 0.44 grams per cubic centimeter. And we need to get it down to 3.16. If we add water, we should get it down to 3.16. Okay. I don't get why that's doing that. If you're not seeing this, for some reason it goes down. And then if I add a little bit more water, I'm just trying to get it at 3.16, but it doesn't like that value. There we go. That's the value we want. Now let's just make sure. 1.33. 1.33 radii. Yep. Okay. Now on to our last moon. Not our last moon. I have 2 more to go after this one. So our next moon, so B6. Okay, Earth masses. This is a lot less massive. So let's see how many digits it truncates to. 0.00054653276. Okay, it gave me 6 digits this time. Okay, so it's starting out at 4.07. We want to get this to a density of 2.2. There we go. That's the right value in density. 0.109. Everything's correct there. Now for B7. Let's call this Renault B7. And it is, in terms of Earth masses, 0.0042427296869. Okay, we're starting out at 7. And we need to get down to 2.76. Trying to get it back up there by adjusting these. Sometimes it doesn't behave the way you think it should. There we go. Sometimes you just gotta work with it until it gets close to what you want. And just to make sure we did everything correct, yep, that's perfect. And now I can say that this is the last of the major moons. We're now B8. In terms of Earth mass, this is the least massive of the bunch. 139742051. Okay, it's still cutting it off at 6 digits. That completely iced over the minute I added even 1% water to it. And we're needing to get to 2.70. Going the wrong way for some reason. There we go. That's the value that we want, 2.70. Last confirmation of the major moons, 0.0658. Exactly what I have to that number of digits at least. Okay, it's time to save. Test. Replace it and let's reload. Test 1 can be deleted. And test. Here we go. Now it's time to do the orbital adjustments and see if I can correct a few things on the fly here without messing up too badly. And if anything goes wrong on the stream, I'll just fix it off stream. So this is the one that's the least calculated value of the distances for the major moons. It's 95,565,000 meters. And it gave it some weird truncated value. I dislike that. there any way to just change this to kilometers? Make that a 5? No, it's going to force me. Force my hand here. 95565. I'll just make sure it matches what I have on paper now. Okay, it does. Sometimes you just have to change units to make it work. Start off with that eccentricity, and we have a inclination of 2.53. An argument of periapsis of 151.4. 115. Let's change this to the value it needs to be, which is 0.009671. No, it didn't round it up to 0.01. That's still not a thing. So let's use the true anomaly instead of the mean anomaly. That's 359.29. And it does round that one down. Okay, and finally, we tidally lock it, watch the days go down. Now this would only have a 14-hour day. And on to the next one. Let me just make sure. Yeah, it kept the right kilometer amount. Okay, let me do some quick and dirty rounding. Quick and dirty conversion of everything from meters to kilometers. Because it looks like kilometers enter in a lot more accurately than meters in this game. 151,699. And it's all going to round up to 700. Okay. Point 2. And we're going to have an inclination that's what it would be before I do the minus 2.16. I was entering that into the wrong field, wasn't I? 0.02. Okay, so here we go. Inclination, I just entered that in. Did the quick calculations in my head. Argument of periapsis, we're on that. 354, it's going to round up to 355. 115. And this will have a eccentricity of 0 after it rounds. So true anomaly would be 1.167, and it has an orbital period of 1.24. So this will end up being 1.24. On to the next one. You see how they're all basically aligning with the equator of the gas giant that we have. That will happen. Okay, the next one is 183771. Okay, 0.2. And the next one. And then we need to subtract 2.16. But this digit gets rounded up to 3. Five 0.66. And then we have the rate ascension of 115. This is another one that would be 0.009, but it gets rounded to 0. Okay. .196, which becomes 197 because there's a roundup. Everything's starting to come together. The moons have a sizable gap between them. Now, technically, these moons are a little close to each other. B2 and B3 are a little close to each other. But I think the orbital mechanics are going to keep the system together. 213, 245, 246. And this one's going to have a inclination of 24.73. That will be a 7. 6 minus 1, 5. So that becomes 22.6. All right. And then argument of periapsis is 75.53. Yep, it rounds. All these are going to round down to 0 for eccentricities, I believe. I can just mark them as 0. And then we're on what? 4? 4 has a true anomaly of 359.7. We're looking good. The spacing looks realistic. And 5 is going to have a 240.805, but rounded up to 6. So that's going to be 0.02. And the inclination on 5, that's going to be 24.72. And there's a 6 after this, but we need to subtract 2.16. So that will be 6. That is 6 minus 1 is 5. 2. And that rounds up to 7. But since it's going to truncate anyway, didn't matter. Not really truncate, it rounded. And then we have an argument of periapsis of 192. The two most important values for this, inclination and right ascension of the ascending node. This needs to be correct, and this needs to be within a degree of similarity. I almost said simularity. Sorry, I need to get a drink. I'm so dried out. And then this one is the 5th one. Has a eccentricity that's going to round down to 0. And then that means we use the true anomaly instead of the mean anomaly. 351.67, which rounds up to 352. Now I don't remember if my last couple planets I tidally locked, so I'm going to have to make sure. Yep, I forgot on a few of these. I believe on 2 I did tidally lock that one though. Okay. Moving on. The 6th one. Number 6, we have a $271,926 kilometers. 0.02, I mean. And on 6, the inclination is going to be 24.66 at first. That will be a 0. That will be a 5. That's a 2. This rounds up to 1, and it all falls off. Okay. Gotta remember we're on 6, not 5. Argument of periapsis is 18190. And then this will round down to 0. And that's 57, which will round up. Will this round up to 58? Oh, it doesn't. Well, that's good to know. And now, just to be certain, we go ahead and tidally lock that. Okay, Renau B6 is done. Now it's on to Renau B7. Renau B7 is going to be 301,356. And then 876. Hello, Jaden. We are right now building a moon system. You are right now the only person. The other person who said he'd tune in is right now probably asleep in the UK. I'm building a moon system for my custom system. And you left. So 24.56, that's a 0. It's going to be a 4 and a 2. And this would round up to a 1, but it doesn't matter. Who's your friend, Jaden? Okay. And what's the argument of periapsis? That is 49, which will be rounded up to 50. And then change this back to 0 because what I have on paper is just going to round down to 0 anyway for the eccentricity. And true anomaly will be 255. Okay, that orbit is complete. Now I just have to tidally lock it. So from 24 days to what? 3 days? 3.48 days. So Renau B8. This is the last of the major moons for this custom-made gas giant. So it is going to be how many kilometers? 333,972. And I have some meters and change on my papers, so this is going to round up to 73. XX Beast Killer. His picture is a spring trap. Well, I can look at his channel. No promises if I'll subscribe. I'm looking it up on my phone now. Okay, so he has the fan-made picture of Springtrap. Yeah, I see him. He has only a few more subscribers than I do. Yeah, no harm in subscribing to a small YouTuber. Okay, the eccentricity is going to be set to 0.2 for right now. That way we have the argument of periapsis opened up to edit for us. And then to get this right, the eccentricity needs to be within a certain degree of 22.4. That's the degrees of the plane where the equator of the gas giant is. And this one, since I messed up on the degrees earlier, I have it on paper as 22.57, but that needs 2.16 degrees taken away from it. And there we go. That's the inclination. We're nearing the end of the major planets, and then we can get into the little minor planets that circle around it. So the argument of periapsis, that is 225, and it's going to round up to 226 degrees. With 115 as the right ascension of the ascending node, and the eccentricity will round down to 0. And now, not the mean anomaly, but the true anomaly needs to be entered in, which is 72 degrees. Now everything looks so perfect. It's okay, we all start off at different degrees of skill. I'll look through his videos later. Okay, see ya. Alright, now we're tidally locking this planet. It's 4 days per rotation. So that is our moon system for this gas giant. It's a little bigger than the last moon system. But this one, I did end up combining some of the planets on Dodonct. And I haven't went through that process on Renau. So this could change if the simulation shows that some of these moons become unstable over time. So this is our initial. Let's go ahead and save this. Save the simulation under test. And I have one more moon, it looks like, to add under the B column. It's not going to be one of these larger moons. It's going to actually be what you call a Lagrangian moon. It means it's in the same orbital path as another one of these bigger moons. Let's do random small moon. You started out here at first. I know I just saved, but I need to save again because I won't be able to edit any of the statistics of the moon. And now I have to reload. Test. So let's call this, I know, so original, Renau B8-L4 because it's in the L4 location in the same orbit as B8. Now this is a dinker of a moon. 7.14235, and it's so small because only, I think, a couple hundred or maybe I'm not even sure how many kilometers wide it is. I think it's only like 12 or 15 kilometers wide, which is why it's so small. Yep. There we go on that one. And it needs to be, yeah, I'm not going to be able to get it as small as I want. Well, maybe I can. It needs to be 2 grams per cubic centimeter. So mostly made up of water. There we go. And now we can edit now I can edit the orbital statistics, which are going to be almost exactly the same as B8. It's 33397.3. Set that to 0.02 for right now. And what did I have B8's degrees? It's inclination of 22.4. So 22.4. And this is 226 for the argument of periapsis. And finally 115. Now we're in the same plane. And I just have to adjust its eccentricity down to 0. And its mean anomaly will be 132. And now it is 60 degrees ahead of B8 and should stay pretty close to that location for the foreseeable future. We'll see how it gets affected by the other moons in the orbits. It might get thrown out. You never know. And if that happens, that's fine. So now I can save again. Save it under test. Okay, I am done with the major moons, and now I'm going to add what could essentially just be called asteroids that got captured by this planet. Not sure if I want to do all of these. I have 11 in prograde orbit and 14 of them in retrograde orbit. I might add a few of them on camera and then add the rest of them off camera a different time, just to show the process of how it's done. I hate this cold weather that we're starting to get. I feel like I'm already getting a cold. Excuse me, have to take a drink here. Alright, so let's start adding some more. I'll do the first 3 prograde moons. I'll just add them all at the same time, name them Renau C101, Renau C102, (103). I could actually, I guess, use a random asteroid. Well, that would probably be better, because these are a little bit large for what I'm looking for. Oh well, I'll just adjust the masses later. 3 more moons for the retrograde moons, and this will be Renau C201, Renau C202, and Renau C203. And because we can't edit any of the orbital statistics when they're first added, I have to save and reload, and then we'll be able to change those moons to the right positions. No, not save, I meant to hit a load test. Okay. Now for these, since I added the large moons, I didn't mean to. I need to adjust these to what mass I want them to be. And that should change them from what they look like now to the more reasonable mass that I want them to be. And this needs to be in terms of Earth mass. 1.02667 E -8. There we go. That's much more reasonable than what it was. So that's only about 15 kilometers wide right there. And it's not a sphere, so it's a potato shape. And what do I want? This is going to be 2.5 kilometers wide, so it's kind of an icy asteroid. Or not kilometers wide, 2.5 grams per cubic centimeter. And that's what we want. Okay. And then this one will have the orbital characteristics of... I'm not going to change any of the inclination values that I calculated earlier for these, because these are captured objects. Captured objects aren't going to be within necessarily the same orbital plane as the other moons, the inner moons, or the inner major moons. Captured objects will most likely be on a highly inclined orbit and possibly very eccentric orbit. Meaning I don't actually care if these moons stay within the orbital grasp of this gas giant forever. It's just creating them for right now, for at least the complexity and the look of realism. The eccentricity is actually something that the game can handle. So 0.194, where does that truncate? Okay, it rounds up to 0.19. So that's going to be the eccentricity. I don't have to actually change that now. And the inclination is 32.34. And that's taken from like the statistics of the moons of Jupiter and the moons of Saturn. They're usually close to around 30 degrees inclined to the orbital plane, to the ecliptic. So I took that, and my numbers are all between 30 and 40 degrees inclined for these moons. And then where's my argument of periapsis for this one? 3, 2, 6. And then there are no specific values that actually have to be kept to on this. You could have a captured object that's on the ecliptic. I just don't in this circumstance. I don't know why I copied over the period. I didn't need to write those down for any of these moons. Okay, so this one I would actually need to use the mean anomaly since I have an eccentricity that's non-zero. 1, 2, 8. I did something wrong here. I think I forgot a 7 in this number here. 11778699. That's better. It looks like it's far out there, but the distance at which many of these objects can be is several, maybe even 100 million meters or kilometers away from the planet. The center of the planet, that is. So that's where this one is. And since this gas giant is 11.4 AU, that's 11 times the distance from the Earth to the Sun. Yeah, that's a pretty long way out there. The further you get away from the parent object, the further out a moon can orbit that planet. Okay, so Renau C2 is where we're at now. Oh, it doesn't really matter for these ones, but just for consistency's sake, I might as well tidally lock this moon. Yeah, it's going to take it 49 days. Some of these other moons could take years to orbit the planet. Hi, She. How are you doing? So, let's go ahead and change the mass of this moon. What does it need to be? It's a little bit too large to be one of the captured asteroids, so let's reduce the mass. It's going to be 2.71811 times 10 to the negative 9. Okay, that's a little asteroid now. That's what it needs to be. And what's the density? 2.17, we need to add a lot more water. Okay. Let's take away some silicon. There, I shot over. There, 2.17. Oh, I'm building a moon system for this gas giant here. I already have a lot of the inner moons done, and I'm just taking care of some of the outer moons that are just captured asteroids. And then I'm going to put the ring system on this. I haven't put in the rings yet. So let's do the orbital statistics for this. Okay, this orbits 178, let's say 2, 3, 4, 9. I have a feeling I missed a number there. There, that's closer to what it should be. And this one has a noticeable eccentricity. And what's its inclination? 36.2. And this one has an argument of periapsis of the 78. Can't type today. 8 point. Okay, that just rounded up. 110. And its mean anomaly is 358. Yep. So this one, even though it started out on the outside of the one that is orbiting closer, because it's eccentric, it now orbits inside of C101 and also goes outside. But it takes longer to orbit the planet. It takes 50 days, where this one takes 49.9. So they're close, but it's pretty good. It seems to handle well. I let it sit all day sometimes while I'm out and about. Yeah, you should test it on max settings. It probably can handle it. Not sure if every computer can handle it, so if you don't have a powerful graphics card or CPU, might not want to do it. You could hurt your machine. And just for consistency's sake, I'm going to tidally lock this one so that it's 50 days. Yep, there we go. So this is the last of the prograde moons here. And Terraria? I haven't really got into Terraria. How is Terraria? Okay, 6070676. That should be out past the last moon. Not sure it's supposed to be out that far. Did I type it in right? Yeah, it is supposed to be out that far. It looks like it's out pretty far, but the hill sphere for this planet is probably out to like right here. We could have moons that orbit like way out here and still don't fly out and orbit the sun. Or the star in this case, since it's not called the sun. It's called Yontai. So let's continue C3. Did I forget to change the mass of this one? Yeah, I totally forgot to. This needs to have its mass changed to 7.85136 times 10 to the negative 9. And then make an elliptical moon that goes inside the other moon's orbits. Because I don't want to mess up all the moons. Oh, you were looking at all this over here? There are a lot of objects that are being simulated. This is the other moon system. I built this one off screen before. Okay, back to the moon system we're working on currently. Like I said, this is going to be the last of the prograde moons. I'll work on the 3 of the retrograde moons and then do the rest of the captured objects off screen. Oh, I've saved this simulation. Don't worry. I've saved it several times. I don't want to lose anything. Kind of paranoid about losing everything. So this needs to be about 3.21 grams per centimeter to be the right density. Let's remove some iron. 3.23. I feel like I have too much iron on this one. Maybe not enough. It's kind of odd how sometimes when you lower something, it goes up. Okay, 3.22, that's close enough. I don't have the patience for that. And where was I in this? Okay, got it out that far. That's the correct amount. And it's an eccentricity of 0.266. And an inclination. Yeah, this is probably the most inclined moon of the entire system. 39.89. 212.67 for the argument of periapsis. What's this? 91? And it has a mean anomaly of 57. And then we lock its rotation. Let's see how it looks with the other moons. Yeah, it looks kind of far out there, but that's the way it's supposed to be. Okay. And now on to these retrograde moons. What is the mass of C201? 3.35085 E -9. And we want this one to be, oh, I can't get it down to 1.1 or 1.5 grams per cubic centimeter. But I can get it down to 1.22. That will have to do. And let's go ahead and edit this 1523074. Yeah, these ones, the main feature is that they're going to orbit the opposite way of the other planets. They're called retrograde, which is why they're called C. It has the C201 because these are retrograde. They're a completely different type of moon. Inclination, and this is what stands out with retrograde moons, is they have an inclination of greater than 90. That means they orbit in the opposite direction now, but when the inclination becomes greater than 90, that's how you get a moon that orbits backwards. If you have it 180, it's completely opposite and uninclined at the same time. I know it says it's a non-zero inclination that's uninclined. Makes no sense. (214.54) for the argument of periapsis. And what is the right ascension? 282. That's going to round up to 283. And now the mean anomaly, 5.6. Yeah, that one's highly inclined. It orbits inside all the other captured objects. And also outside their orbits too. Doesn't intersect with any of them. Okay, last thing for consistency's sake. $39.5 days. So now on to the next moon. And then I can add the ring system and we can see how it looks when it's simulated. And I'll add the rest of the smaller moons outside this simulation. I just want to add these moons for anybody who's curious in how it looks when you're adding moons that could be considered captured objects to what you're trying to make as realistic a simulation for a custom system as possible. Let's go ahead and make this an accurate mass. .19868. 10 to the -9 should do. And this one needs to be 2.52 grams per cubic centimeter. Oh, I thought it was perfect. There we go. And what distance? 177141148. Okay, so what is the eccentricity on this one? It's 0.266. That rounds up. Okay. 127.18. Then the argument of periapsis will be 340.18. And the right ascension, that is going to be 98.49. And finally, for this, mean anomaly will be 24.3. We tidally lock it and it should be done. Okay, we're on to the last moon. So for this one, it is 3.37444 times e to the -9 times 10 to the -9, I meant. That's actually kind of on the larger end. Did I type that incorrect? Oh, it hasn't updated the density. Yeah, that's closer to what it should be. These should all be between 10 and 19 kilometers once they are configured correctly. And that's the key, is making them between those values. And this one I can actually get it to 1.38 grams per cubic centimeter, but it's going to be an icy snowball. A dirty snowball, I mean. There we go. Okay, so this one, yeah, all of these moons are a lot closer to the planet than the prograde moons, honestly. Okay, that looks correct. 0.309 should truncate. 123.3. And the argument of periapsis is 124.91. Right ascension, 112 exactly. And now for the last thing, the main anomaly is 269. That didn't move it very far. Let's lock its orbital rotational period. Okay. So that was the last of the retrograde moons. Now it's time to give this gas giant a ring. I have the numbers written down. That should give us the right ring. And the ring needs to be, there is some math behind the ring system to make it between, I believe, 1.34 planetary radii from the center and like 3 planetary radii from the center. I need to move the YouTube chat, it's right in my way. Okay, so this needs to be closer to the planet than 7,000 kilometers. Needs to be at 426, I mean, 86. Let's see if it allows a decimal point. I didn't think it would. Can't really tell the difference between 1 or 2 kilometers anyway in this game. And then its outer radius needs to be 77726. Let's let the game decide what gaps need to be in the ring. I'm not sure if it's very accurate in doing so. And the material should be water ice. I believe that should add an accurate ring, but everything's kind of dim, so I'm not sure if we can see it very well. Let's go ahead and try. It's kind of faint, but maybe you guys can see it against the background, the brown here. Can't really make out all the planets or all the moons that are within the ring system, but hopefully those moons keep this ring stable. All right, time to save this. Actually, no. We need to save this under test. I need to get rid of the ring system, sorry. I need to save this under new. And now I can add the ring system back onto the planet. Okay. Let's see if I can get it any brighter. Show ring gaps. Yes. Yeah, it didn't get any brighter than that. Now I can save this. Now that it's saved, let's go ahead and see how it looks. I know everything looks crazy there, but that's how it has to work sometimes with Universe Sandbox. When you add an object, you can't really edit the orbits until you've saved it. So it looks messy when you don't have orbits view on. If you just have the trails view on, looks like things are going everywhere. It looks like that for my entire system. Even out here you can see where I had to do it. Within this planet, yeah, it's all over the place. Back to Renau, we have reached that moment where we're going to land on one of our moons and see how things look. I know it's kind of dim, so I'm not sure if we can make out the ring system very well. I think I'm going to have to get rid of some of the water ice on some of these planets because there's too much. Their atmosphere, the water's being stripped from them, they have a cometary tail. Let's see how these moons on the inside are faring. Are any of them like being ripped apart or heated up too much? these look relatively stable on the inside. They should keep them they should keep themselves stable because they're all in orbital resonance with each other. And these moons are also in orbital resonance with each other too. Okay, let's see if any of these planets are still losing mass. I saw that some of them were when I initially turned on the simulation. I'm not seeing anything that resembles a cometary tail, so maybe we're good now. Well, that is me building a moon system. I know it was me just mostly typing in numbers and stuff like that. I wish I could show you guys how you calculate those numbers, but that would be a video in and of itself. And I just don't have the script or all those figures that I have memorized. Oh, we have some problems in the inner ring system. See, this is what happens after you've built the system, is you have to do maintenance on it. Stuff like this will happen where the orbits get all messed up. Probably too close to the moons. The inner moons are too close to the rings. I might have to move some of these moons out, but that will probably be an off-camera type of thing. Once I've figured out what needs to be done, some moons might have to be deleted or combined with other moons. But the goal is to get it to something like this, where stuff is relatively stable for years of in-game simulation time. And you can even get it to the point where even this system right here is stable, where you have a moon of a moon. Found out that having a moon of a moon, if the moon is retrograde, it's more stable. Yeah, none of these planets are having trouble. So I'm guessing what happened is I have the inner moon orbiting too close to the ring system. So that will have to be an alteration of this planet's ring system over here. Moon system, I mean. Back to the drawing board, as they say. Well, I am going to go ahead and end this stream here. I think I'm losing my voice. Thank you all for watching. Probably in a few minutes I'm going to start up a peaceful stream so that you guys can just watch something simulate while I go do something else. So, thank you for watching, and you guys have a great night, or morning, depending on where you are. Bye-bye.